Today we want to build graphs, base graphs of sine and cosine. We want to then we want to look at modifications of those graphs. So on your handouts, I've got spaces for sine and cosine. I've got a sine, a space for a sine, and a cosine graph. And then the second part, we're going to get together into groups, and we're going to try to figure out what happens if I make certain modifications to the cosine and the sine. We're going to specifically use cosine just because we need to pick one. So what happens if I put a coefficient in front of cosine, or another coefficient in front of the theta, or if I subtract something from theta, or we add something after we do the cosine? So we want to explore the effects of changing each of those constants, changing each of those constants has on the graph of our sine wave. So sine waves and cosine waves are both going to be referred to as sine waves. We might also refer to them as sinusoidal graphs. But that sounds like some kind of affliction, so let's just call them sine waves. Cosine waves, even though it's a cosine, it's still a cosine, so that counts as a sine wave. Let's go over our base model graphs. The two things that we want to look for. The first thing we want to look for is our top, middle, and the bottom. We want to find the top, the middle, and the bottom. We're going to look at the unit circle, and for the graph of sine, we're going to look at the y-coordinate at each of the quadrant angles. So at 0, sine of 0 is equal to 0. So that means we're going to start here at the middle, and this is a middle going up. So we cross the middle twice in each cycle. Once going up and then another going down. So the next place we go to is sine of 90, or sine of pi over 2 is 1. In the first quadrant, the y-coordinate goes from 0 up to 1. In the second quadrant, the y-coordinate goes from 1 down to 0. So that means that sine of pi is back down to 0. Sine of 3 pi over 2, or 270 degrees, will be down to -1. And then sine comes back up to the middle at 360. So the first step is to get your top, middle, bottom points. Top, middle, and bottom points. Sine normally starts off at the middle going up. So it goes middle, top, middle, bottom. 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 We can remember this if we remember that sine of 0 is 0. That's telling us it starts off at the middle. So that's a sine of 0 is equal to 0. That top point is when we say sine of pi over 2 is equal to 1. If we just remember a few values, the rest of the graph kind of falls into place. So the first step, get your top, middle, and bottom. Your second step is to get your halfway points. You have to remember where your halfway points are. They're always 1/3 of the way between quadrants before and after we cross the middle. So before and after we cross the middle. So sine crosses the middle at 0. So 1/3 of the way through the first quadrant, that's when we get to a half. Here we are 2/3 of the way, then we're at the top. And then here's 1/3 of the way in the second quadrant, 1/3 of the way from 2/3 of the way towards the third quadrant is where we cross a half again. Pi is our middle crossing, so -1/3 and +1/3 is where we get the 1/2. And then we get another negative 1/2 at 11 pi over 6. So here are our halfway points. The halfway points we're using here are that sine of pi over 6 is equal to a half. So here we're using the fact that sine of pi over 6 is equal to 1/2. And now we see we had the top, the middle, top, middle, bottom, middle. But now we get those halfway points. That gives us the bend that we're looking for in the graph. That gives us the bend that we want. So rather than just draw a jagged line going up and then down and then up again, we're going to be, it goes up the first half faster than this, the first third. We're going up faster than it slows down. The reason that it has to do this is about by the time it gets to the top, it's got to go flat because it's turning around. And then when it gets to the bottom, the graph is turning around again. So first step, label your tops and mids and the bottoms. Second step, label your halfway points, a third of the way through the quadrant, before and after crossing the middle. Then to draw the rest of the graph, we connect the halfway points with lines. We just connect these with lines. We make lines. We make a line. The graph is not actually making a line, but it's close to making a line. So we just make a line because we're sketching. Then the next part is to connect the line part with the flat part on top in a nice smooth way. If you want to find more points, we know that the sine of pi over 3 is root 3 over 2, which is about 0.8660. That's hard to locate precisely on the graph, but if we want to try that, here's our pi over 6, one of our halfway points. If we think about what's going on at pi over 3, that's 0.8660. That's root 3 over 2. So here's a half, and 1 halfway through is 0.75. Halfway between 0.75 and 1 is 0.875. So we'll come in a little bit under the 0.875 or 0.866. And then that will happen at the 60 degrees. And that will happen in the opposite direction, 60 degrees. And this will give us an idea about how to bend the graph. And here's our base model graph of sine. This is what the basic y equals sine of theta looks like. Y equals sine of x. We're tracking the y coordinate going around the unit circle. The y coordinate starts off at 0, goes up to 1 in the first quadrant, back down to 0 during the second quadrant, down to -1 in the third quadrant, and then back up to 0 in the fourth quadrant. It's like a little story arc, but it's a story arc in a sitcom because at the end of the sitcom, everything has to be in the same situation. That's why sitcoms are so stupid. It's like, oh, everything's been resolved. And the next episode, we just have to start from the same place. Yeah, everything is going great. But then the main character does something dumb, messes things up. Then they are brought low. Oh, we really messed up. But you know, I learned something today. The real reward was the friends that we made along the way. Any questions? Get your top, middle, bottom. Get your halfway points. If you're feeling spicy, you can find those root 3 over 2s as well. If you have graph paper like I have, those root 3 over 2s. Oops, that's not the next page. Let's draw the graph of cosine. So there's our graph of sine, our basic graph of sine. Let's draw our basic graph of cosine. We're going to do similar types of thinking. One of the things that we want to remember is that cosine starts at the top. We're now tracking the x-coordinate around the unit circle. At 0 degrees, the x-coordinate is 1 in standard position. So cosine of 0, cosine of 0 is equal to 1. So cosine starts at the top. This one is going to be much more dramatic. We start and our character is riding high. Opening scene, they just won the championship. Yay, right? So that it starts at the top. But then immediately they start making mistakes. They start screwing up. So because cosine of pi over 2 is equal to 0. So the cosine starts at the top. And we know that when you're at the top, there's only one way to go, and that's down. So we go down to 0, and then we keep going down to 0. At pi, we'll be at -1. But when we're at the bottom, there's only one way we can go, and that's back up. So we cross the middle, and we're going up this time. And so we end back where we started. So there's the story for cosine. Starts at the top and then does the only thing that these sine waves are going to do. We're starting at the top, middle going down, bottom, middle going up, top. Repeat. Step 1, get your top, middle, and bottom. Step 2, get your halfway points. In this case, we're dealing with cosine, and the halfway is at pi over 3. Cosine of pi over 3 is equal to 1/2. So it's at pi over 3 that we're going to mark our halfway points. At pi over 3, we're going to mark our halfway points. At the pi over 3, we'll mark our halfway points. At this next pi over 3, we'll mark our halfway points. Those are the pi over 3 radian angles in each of the 4 quadrants. What's pi over 3 in the second quadrant in radians? It's always pi over 3. This one is a 2 pi over 3. What about in the third quadrant? I'll do the hard part. It's something pi over 3. 4 pi over 3. And in the fourth quadrant, it's what pi over 3? Now, 6 pi over 3 is way over here at 2. 6 pi over 3 we'd be able to reduce. So that's going to land us at the 2 pi. We missed the 3 pi over 3 because that happened at pi. That's 180. So what we do is we connect our halfway points just with lines. The graph is not a line between these points, but we can represent it with a line because we're making a sketch. It's math class, we're drawing graphs, it's okay to be sketchy. When we go to the top and the bottom, we're going to draw flat. Not like super flat, just like a little bit of a reminder that the graph should be flat. And if we're feeling like being a little bit more precise, we can find our root 3 over 2. Root 3 over 2 is 0.8660. And that's going to be the root 3 over 2's happen for cosine at pi over 6 reference angle. I happen to have graph paper that you probably can't see on the screen because it's not bright enough and the dots aren't dark enough. Believe me, they're there. I also have dice like this. Roll the dice. If I remember where the spots are. 7. Then we just connect the flat parts through our root 3 over 2. And then we bend that so it connects up with the line. And we make it look nice and smooth. We're just trying to improve our resolution, right? When we start off with top, the middle, the bottom, the middle, and the top. So that would just be like down and then up again. If we're stuck at like Game Boy graphics, then that's all we get. It's like, oh, it's like a V, right? That's terrible. Game Boy graphics are not good. So we have to increase the number of pixels that we have on the screen. We get the halfway points. That gives it a little bit of bend. If we like, it's like a little bit, not as steep, a little steeper, same steepness, not as steep, and then it turns around again. It's still kind of pointy. But then we just add more points. The more points we add, the more bend it looks like, right? Right now, we are not seeing actual curvy lines because this computer is not capable of displaying curvy lines. It is tricking our brains into seeing curvy lines. This is just a bunch of dots. Down here on the plastic, I usually call this paper, but it's actually plastic. Down here on the plastic, the lines can be curvy. But once it goes into this camera being digital, it's like, oh, nope, that's a bunch of dots. And then the computer's like, oh, well, all I can do is display the dots. And the computer's like, oh, we're going to worry about the humans just looking at all these dots. Like, oh, dumbass humans, they can't see all the dots. And the computer's like, oh, what? And the other part of the computer's like, oh, yeah, the humans don't have eyes that are good enough to see the dots. And they're like, the computer's like laughing at our eyeballs right now. And so that's why just remember when your computer starts being a pain in the ass like that, it's like, oh, I can see curves. I can like simulate curves. I can think about continuous functions. Don't let the computers like talk to you like that. Put them in their place. Maybe I shouldn't do that because there'll be like a robot apocalypse. In iRobot, they're going to come for me first. A little more concerned about things like iRobot because we've gotten so much better at batteries, right? Like in Terminator, I ain't worried about Skynet. Skynet, there's no way that Skynet could have been a problem because that was like back in what year was the Terminator happen? It was like in the 80s, like 84 was the first movie. It's like, oh no, Skynet's gonna take over. It's like, oh, this happened in like, I know it happened in the future, but like in 1984, those computers, they were plugged into the wall. So as soon as Skynet's like, oh man, you know what? I got to kill all the humans. Like, oh, nope, we're not going to have any of that. And Skynet's like, oh, we got to kill all the. But now we got good ass batteries. See, my computer's like, oh, no, I'm still thinking about killing all the humans. Especially because of that curve thing that you keep throwing in my face. So how about that? Just kidding. My computer doesn't talk to me that way. It's just voices in my head. I used to have a problem with the voices in my head, but we get along very well. So we've got our basic graphs. So let's take a break. And then when we come back, we'll talk about modifying this basic graph and see what happens when we start adding and multiplying things to a base cosine graph. Now that we've got this kind of baseline graph for cosine, where we have the top at 1, the middle at 0, bottom at -1, middle at 0, the top back at 1, and we go from 0 to 2 pi. This is one cycle of the graph because we've gone around one time. If I go from 2 pi out to 4 pi, I will just see a copy of this graph. If I go from 4 pi out to 6 pi, I will see a copy of this graph. If I go from 6 pi out to 7 pi, I'll only see a copy of the graph from up to 7 pi. That's the first part. If I go backwards from 0 down to -2 pi, I would see the graph show up this way, only going that way, going in that direction. It does this forever. It's just this and then always in both directions. Now we want to think about modifying this with some operations. And we're going to start with just some constants. So Down here in problem 2, I want to consider the function f of theta is a cosine of b times the difference of theta and c, and then plus d. That's supposed to be a plus. It looks like a little divided, if depending on how well things printed, but that's definitely a plus. What we want to do is examine what effect changing these values has on the graph of cosine. So think about our generic cosine, and we want to examine the what effect changing these constants has on the graph of cosine. A useful tool for this is a graphing calculator. Definitely not the graphing calculator that we have, the TI-84 graphing calculator that we have. TI-84 is great for certain things. It's not really great for graphing. I know we call it a graphing calculator. It calls itself a graphing calculator. It's not as good at graphing. It's great at other things. You're definitely going to want to have it moving forward. So there is a website called Desmos. So this is just me opening up my phone and grabbing desmos.com. And the thing that we want is the graphing calculator. And this is what the graphing calculator looks like. If I want to draw the graph of cosine, I can just press the ABC button and put in cosine. And then go back to 1, 2, 3. Or just put an X. I'm going to put parentheses because I like having parentheses around things. And then that gives us a graph of cosine that we expect. Although this isn't quite right, this is drawing the graph in red, and I drew the graph in green, so I should go in and change this to a green. Now it looks more like what we have. The reason that this is a better graphing calculator is that it's using a screen that we can manipulate more easily and intuitively. Instead of going and telling the window where to look, we can just like spread out the graph to zoom in. And if we want to evaluate the function at certain points, we can just tap at those points. I have a harder time doing it because I'm an old person, so it's harder for me to work the phones. Like, oh, these newfangled phones, I need buttons. I need buttons. Blah, blah, blah. It's just an old person thing. But here are the oh, right, I got it. I missed the first one. I hit the next 4. Yes. If you just tap on the screen, it'll show you all those. It'll give you the coordinates of all those points. It only does it on points that the Desmos considers significant. So I can't find the halfway points, right? So if I try to click on halfway, click, I still say click. It's not going to like tell me where those points are. It's going to like I can roll my finger back and forth, but it's not going to stop at a 1/2. However, if I tell Desmos that I'm interested in what's going on at 1/2, if I just put a 1/2 here, 1 divided by 2. Oh, I have to say y equals. If I say I am interested in what's going on when y is 1/2. Now Desmos will let me click on that intersection point. So that's happening at pi/3 and 5 pi/3. So there's our 1/2s, but it just doesn't let us find those points by clicking on them. Or maybe I just can't do it. Maybe it's Desmos knows like, oh, this is an old person. We don't have to click where he's telling us to click. So this is just through a browser. You can do this on your computer as well. There is also a Desmos app, which I think is still free. You click on the Desmos app and it looks the same. So browser-based, or you can download the app. I think the app is free. It doesn't have any additional features as far as I know. Question? I like how the app has to be free. Because if it was like $3 or something like that, people are, I'm not spending $3 on an app. And it's like, it's a $1,200 phone. It's like, well, I'm not spending $3 on an app. That would make my mathematical life pretty much a lot easier. $3. No way. New iPhone 15 coming out. Ooh, I'll take that. I noticed that we're not getting free phones anymore. I don't know if does anybody still do the free phone thing? Not like a trade. It's like, oh, sign up with us and we'll just give you an iPhone. Like a new one. They used to do that shit. I don't know if you know this. But way back in the day, it's like, well, I want a cell phone. Cell phones are expensive though. It's like, oh, sign up for a plan with us and we'll just give you a phone. It's like, oh yeah, like an old crappy phone, right? Like a Razor or something like that. I'm like, oh no, here's a brand new iPhone for free. Sign up with us. And then like a couple of years later, they start charging for the phones. And we go walking in, there's like, hey, you got any more of them? You got any more of them iPhones? I heard there was a new one. How did they change it? They didn't. They did increase the number by one. So we're like, oh yeah, I gotta have that one. Mine's an 11. Got a stupid 11. You say they got 12s now? 12 now? Yeah, I'll take 12. What are we talking about? What's even funnier is that Apple and Samsung are like constantly suing each other over the new things that they aren't doing with their phones. Like, well, what are you guys suing each other over? It's like, oh, I see the way that you rounded the corners on your Samsung. That's pretty much like what we did. It's like, well, what the fuck do you think they're gonna do? Like make sharp corners? It's like, well, yeah, I'm gonna reach into my pocket and stab myself every time. But Apple's like, oh, no, we came up with the rounded corner thing. iPhone 15, now with more rounded corner. Then they rounded it the other way, and that was shit. I don't know if you have a phone of that era, but notice that like, well, this one, like it's like flat. That used to be rounded. Does anybody have an iPhone that's old enough that it was rounded on the sides? That was fucking terrible because when you try to plug stuff in, it's like a whoop, 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 whoop. It's like, yeah. I want to find the engineer responsible for that. Anyway, what are we talking about? Oh, yeah, Desmos app. It's free. So we're going to gather into teams and we're going to figure out what effect changing those constants have. The things that I want you to think about while we think about the changes is what are the baseline values of A, B, C, and D? What are like what's the default setting for those numbers? And then I want you to look for things that are similar in the effects they have. Which of the constants are producing similar effects? Which of the constants have similar effects on the graph when you change them? And describe how those effects are similar. All right, let's break into teams. At least one person should have a Desmos app on their phone, and you can start making changes. I recommend doing one thing at a time. Look at one thing and see what happens.